Welcome to a brief introduction to the concepts underlying the practice of steam distillation. I'd like to begin our discussion by asking a question, and that is, what happens when two liquids of an organic nature are not miscible with one another? In our discussion about traditional distillation, we always made the stipulation that our binary mixture of liquids must be miscible. But what happens when they don't actually dissolve into one another, at least not intimately at the molecular level? And the answer is Raoult's law no longer applies to the situation. So this drastically changes the behavior of our system. And we're going to take a look at this in the coming moments and actually discover that it can be useful that Raoult's law does not apply to systems like these. Let's begin by reviewing how it is that a binary system of miscible liquids is expected to behave. You'll recall from our discussions of distillation that if we plot vapor pressure as a function of the mole percentage of two components which are miscible in one another, we can plot the vapor pressure of one of those components at the extreme end of the plot. In this case, we'll make this the vapor pressure of component A. If I plot Raoult's law on my diagram, I must start necessarily at 0 for 0 mole percent and end at its vapor pressure with a line. This is Raoult's law for compound A. I can similarly place another compound, let's call it compound B, where its vapor pressure is at the other extreme of the x-axis. Plotting a line gives us Raoult's law for compound B. Finally, we can apply Dalton's law to this situation, where we acknowledge that at any particular composition, if we are to take the summation of all the vapor pressures of all the components in the system, in this case just the two, we can determine what the total pressure should be above that boiling mixture simply by adding them. And by doing so, we've generated a plot of Dalton's law for the system. This tells us the total pressure above the boiling mixture at any given composition when it is boiling. Recall again that these two principles, these two laws, were our foundation for making an argument for how we could separate two liquids from one another using distillation. When we're dealing with a mixture of two immiscible liquids, however, the landscape of this diagram changes dramatically. And that's because Raoult's law requires that they be mixed intimately at the molecular level, which is no longer the case. So if we reproduce our plot, but in this case we make the stipulation that the liquids are immiscible with one another, they will establish their own vapor pressures independently of their concentration in the mixture. In other words, these plots will no longer be sloping lines which intersect at 0 at the extremes, but rather they will be horizontal lines indicating that the vapor pressures do not change as a function of concentration. This is true for both compounds A and B. Assuming that Dalton's law, however, holds in this situation, what we see is that when we plot the summation of the two vapor pressures, is that we end up with a straight line. Now the potential problem with this is that if we want to isolate these two components, notice that the ratio of components in the mixture above the boiling liquid never changes, which means that by traditional distillation standards, this is not a good technique for isolating these two liquids. And in fact, it isn't. So we can see clearly that there's a drastic difference in the behavior between miscible and immiscible liquids when we heat them up and boil them. So let's take a look at this immiscible liquid diagram a bit closer and think about exactly what's going on here. What it's telling us is that components of immiscible mixtures establish their own vapor pressures in the flask, regardless of their concentration in the boiling mixture, and therefore Raoult's law does not apply to such mixtures. This, again, is not a very good observation if it were our goal to separate these two compounds. And so we wouldn't use a traditional distillation to try to separate compound A from compound B. However, this observation will become a useful and valuable observation when we attempt a steam distillation. So let's consider our goal here where we want to separate a water immiscible oil of low volatility from a non-volatile contaminant. And I will just use, again, as normal, we'll use a little cartoon system here to represent these compounds, where we'll have blue spheres as water, red spheres as the immiscible oil, and brown spheres as the non-volatile material. So again, our goal in this experiment is to take a mixture of immiscible oils and non-volatile material and somehow isolate that immiscible oil. Notice that water is really not relevant to this process at the moment. All we want to do is be sure that we separate our immiscible oil from our non-volatile material. And in this case of steam distillation, water is just going to provide a medium for us to accomplish that goal. Shown here is a schematic of the steam distillation apparatus that you'll most likely use in a teaching laboratory. The apparatus consists of a separatory funnel, which is used as a reservoir for additional water when needed, a boiling flask in which the mixture of oil, low volatility material, non-volatile material, and also the water will be boiled. A thermometer is attached to the device through a still head, so we can monitor the temperature. And you might not be surprised to hear that the temperature in a steam distillation is usually about 100 degrees. From the still head onward, the system is going to look exactly like any other simple still. We'll have a West condenser with the cold water plumbed in through the lower of the two hose barbs and out through the higher of the two hose barbs. We'll have a vacuum adapter to direct the flow of distillate into our receiving flask. Now that we've reviewed how to construct the distillation apparatus, let's take a look at how one functions. We begin the experiment by charging a boiling flask with your materials and a little bit of water. And you'll also add some additional water to the separatory funnel with the stopcock closed in order to provide a reservoir. We'll begin by opening the stopcock very slightly so that the water from the separatory funnel is dripping into the boiling flask. As we apply heat to the boiling flask, the mixture will begin to boil. And of course, as you might expect, water being the most volatile of the compounds within the flask, will get a great deal of water distilling out. But again, remember that the immiscible oil will establish its own vapor pressure in the headspace above the flask, independently of the vapor pressure of the water. This means that if you look carefully, you'll notice that every so often a little bit of immiscible oil also is carried along into the condenser by the moving water vapor. This means that over time we expect to accumulate in the receiving flask a mixture of water and immiscible oil which is consistent and very constant in concentration. As we do so, we slowly deplete the immiscible oil in the boiling flask until at some point this process has been carried out to the extent that all of the immiscible oil has been moved into the boiling flask, and now there's only water and non-volatile material remaining in the original boiling flask. At this point, we can deactivate our still and take a look at what we've accomplished. Notice what we've accomplished is that the red immiscible oil material has been removed from the brown non-volatile material using water as the medium. Now, separation of water from the immiscible oil is very simple. That can be achieved usually by liquid-liquid extraction. And at this point, we've accomplished our goal. And this is how steam distillation works.